When preparing for mathematical admissions tests, such as TMUA, MAT, and the mathematics modules on the ESAT, one of the topics students most often report difficulties with is graph transformations. On one hand, this is a very simple topic. It's taught in GCSE and reviewed very early in A-level mathematics and IB. On the other hand, the way that graph transformations are taught in school is not always the most helpful way to think about them when dealing with the more difficult problems that you're going to encounter on admissions tests. Before introducing a better way to think about graph transformations, let's first review some of the issues with the standard formulation. The standard treatment of graph transformations given in school goes something like this. We have a set of rules for translations, stretches along the direction of the coordinate axes, and reflection in the coordinate axes. And each of these rules are given as the effect of that transformation on y equals f of x, so a general curve y equals f of x. So, for example, to translate by a horizontally, where positive a means rightwards, I take y equals f of x minus a, whereas if I want to translate by a vertically, I have f of x plus a, where again, positive a in this case would mean upwards. We have similar rules for stretches in the x and y direction, and reflections in the x and y axes. Now, already looking at these rules, the first issue with this formulation becomes clear. Namely, why do the x and y direction transformations look so different? Now, this is more of an issue than it seems. It suggests there's something mathematically unnatural about the way we're formulating these rules, because there's nothing special about the x direction or the y direction relative to the other. If you turn your head by 90 degrees, one has become the other. So the fact that they look so different is suggestive that there might be a nicer way to think about things. So the difference can broadly be summarised that the transformations in the x direction go in the bracket, whereas the y direction transformations go outside. So for translation, in versus out. For reflection, out versus in. For stretch, in versus out. And moreover, transformations in the x direction seem to be the opposite of what you'd expect. So I've got a minus a rather than a plus a. Or for a stretch with scale factor k, I've got a 1 over k rather than a k. So as well as the fact that this is hinting at a sort of mathematical unnaturalness, in practical terms it means there's more to memorise and more to potentially get wrong. Now, in terms of why this has happened, the explanation is very simple. By forcing our rules to act on y equals f of x, we are effectively breaking the natural symmetry between the x and y directions. So the x and y directions mathematically are on completely equal footing, but when we insist that these rules are going to be formulated on a curve for which y is the subject, we're privileging y at the expense of x and breaking the natural symmetry between the two directions. So if we can find a formulation which restores this symmetry, things should unfold more nicely. Now, in relation to this, the second issue is, what if our graph is not of the form y equals f of x? So, for example, we know that the natural equation of a unit circle, say x squared plus y squared equals 1, is not normally presented in y equals f of x form. We might want to perform a transformation on a circle. Maybe we'd like to stretch it to turn it into an ellipse, for example. And while, certainly for the circle, if we are so motivated, we could make y the subject at the expense of introducing a square root and a plus or minus, for more exotic curves, it might be more difficult to make y the subject. In some cases, it might even be in practice impossible, and it can make the equation much uglier, even if it can be done. So the fact the rules are posed on y equals f of x graphs is a limitation. We'd like to be able to easily transform all graphs, even if they're not in that form. And the third issue with the standard formulation is, as posed, it can make it a little bit more difficult to see what happens when we have a sequence of graph transformations rather than just a single transformation. And, this specific issue is one of the things which A-level and IB math students most commonly report issues with. So for example, suppose that I want to perform a translation by 2 to the right, followed by a stretch by scale factor 1/2. So if I do the translation first, I know that I take f of x and I replace the x in the bracket with x minus 2. So that is the rule for translation. We have y equals f of x minus 2. But the point that's a little bit confusing is if I now stretch by scale factor 1/2, parallel to the x direction, I know that in the language of the rules, that is f of 2x. So there's some doubling that's going on. But do I double everything in the bracket, taking 2x minus 4, or do I only double the x, taking 2x minus 2? Now, the correct answer is you only double the x. But the formulation in terms of y equals f of x does obscure this fact somewhat and make it a little bit less obvious what the correct prescription is. We can address all of these issues in one fell swoop by subtly adjusting the way we think about graph transformations. The ordinary perspective is that graph transformations are something you do to the curve. You imagine taking the curve and sliding it by, say, 2 units to the right. The crucial insight we need is that this is equivalent to performing the opposite transformation on the coordinate axes themselves. And this distinction is sometimes called active transformations versus passive transformations. Crucially, they are 2 different ways of describing exactly the same thing. So suppose we have the following graph, and we'd like to perform a horizontal translation so that the peak of the graph aligns with the x value that I've highlighted here. So the way we'd normally think about doing this is as an active transformation, which means we slide the curve itself along until it's in the right place. So this perspective, that the transformation acts on the curve itself, is very much the philosophy that's adopted with the school level presentation of graph transformations that we reviewed earlier. Because when we give the rule as acting on y equals f of x, we're baking in the idea that it acts on the curve. But here's an alternative perspective. Rather than translating the curve, we could instead perform the opposite translation on the coordinate axes. And that has exactly the same effect. I've managed to align my key x value with the peak. So it's exactly the same thing, but it's viewed a different way. In other words, if you want to perform a transformation on the graph, it is completely equivalent to performing the opposite transformation on the coordinate axes. They do the same thing because when we describe curves, we're always describing them relative to the axes. But the perspective that the transformation acts on the axes instead, the passive transformations perspective, can lead to a much more helpful formulation of graph transformations. So for example here, let's say I had done my translation by 2, translating by 2 to the right on the curve is the same as translating the axes to the left by 2. So the active transformations perspective, if I generalize to a translation by A, is I've translated the curve right by A by doing this to the equation, and that's the perspective I'd encourage you to move away from. The passive perspective is that you've translated your coordinates. So if I've translated my coordinates themselves left by A, every x coordinate is A less than it would have been. So now the rule is that I replace x with x minus a everywhere where it appears. So it's obviously the case that if I use this rule on y equals f of x, it gives me the same thing. But I could use this rule more generally, even if my curve is not of the form y equals f of x. If I've got some x's, I've got some y's, then I simply replace the x's with x minus a. So we can use this philosophy to formulate sort of opposite passive transformations for all of the transformations we're familiar with. And the beautiful thing is that now the rules for x and y look the same. So for example, if I want to translate by a horizontally, we've already noted we shift our coordinates left by a. So that means I replace x with x minus a. Well, similarly, if I want to translate my curve up by a vertically, I shift my coordinates down by a, so I replace y with y minus a. So no longer is there this sort of violent breaking of the symmetry by forcing everything to be y equals f of x. The symmetry is nicely preserved. There's no more in the bracket, out of the bracket. There's no more doing the opposite. And so similarly, if I want to stretch by a certain scale factor, I do the inverse scale factor stretch on the coordinate axes. And then for the reflections, if, for example, I'm reflecting in the x-axis, it's like I'm inverting, negating my y coordinates. So it's like I'm replacing y with minus y. I'm flipping the y-axis. So the rules are now far more symmetric and far easier to memorize now that we've formulated them in a passive way. And also we've solved, therefore, the second issue, which was that we don't want to only be able to work with y equals f of x graphs, because these transformations can work on any form of graph you present. As long as you've got x and y coordinates, you can make the changes. Now, a quick remark. You might be thinking, well, this is all very well, but we already know from school that the y transformations do look different. Well, let me now convince you that these y transformations are equivalent to the transformations you're more familiar with. I mean, for the x transformations, it's obvious, as we just saw. But the y transformations, you might worry that they look different. Well, let's consider a vertical translation. So suppose I want to translate by 5 upwards. Using our new rules, that means we replace y with y minus 5. So if I did have y equals f of x, it becomes y minus 5 equals f of x. So when I then bring the 5 over, I've now recovered the old rule. So the reason the old rule looked different is because implicitly, after performing the passive transformation, it's like we've rearranged to make y the subject again if it was no longer the subject. And that's why it's now doing the opposite of what we would expect relative to the x direction transformation. So that's why there's this sign difference, because with one you've had to remake y the subject, with the other you haven't. So we can see that we do get the same rules as before. Now, this is also very helpful when it comes to order of transformations. So, for example, suppose I'm thinking about y equals f of 3x plus 2. We can see from the basic form of this transformation that we know there is a stretch with scale factor 1/3 involved in the x direction due to the 3 in front of the x. And there's also been a translation by minus 2 in the x direction due to the plus 2. However, from the school transformations perspective, it's not necessarily completely obvious what order these are supposed to take place in. Now that we've formulated everything as replacement rules, however, we can simply do it and see what happens. So if I do the stretch first, I first replace x with 3x, because I replace x with 1 over the scale factor x. 1 over 1/3 is 3. Then, when I do the translation, I'm going to replace x with x plus 2, that is x minus 2, to do the translation. So because there's already the 3 in front of the x, when I now replace x with x plus 2, I get 3 lots of x plus 2, which is 3x plus 6. So by simply doing the transformations in this order, we can see we get the wrong thing. On the other hand, if I do the translation first, I first replace x with x plus 2, and then when I replace x with 3x, the 2 is sitting there, it's not touching the x, so it's protected. Only the x picks up a factor of 3, and now we get the right thing. So it is also easier now to see how to deal with compositions of transformations, since we formulated everything in terms of replace x or y as appropriate. As well as becoming familiar with this new way of thinking about graph transformations, students preparing for admissions tests in mathematical subjects can benefit enormously from learning a couple of bonus graph transformations. In particular, rather than just knowing how to reflect in the coordinate axes, it's extremely helpful to learn a single transformation rule for reflection in an arbitrary horizontal or vertical line. So let's take the example first of an arbitrary vertical reflection. In other words, can we find a rule to implement a reflection in any vertical line, not just the y-axis? Well, in general, a vertical line looks like x equals a for constant a, because the x-coordinate's the same everywhere. For example, the vertical line that's 2 to the right of the y-axis is x equals 2. The way to find a single rule which implements this is pretty straightforward. If we can identify a sequence of simpler transformations which has this overall effect, we can then simply study what happens if I do then perform those transformations one after the other, and we can take the end result as our rule. So here is a simple set of transformations which will clearly have the effect of reflecting in x equals a. First, we can translate by minus a horizontally in order to bring the intended line of reflection, which was at x equals a, to x equals 0, the y-axis. So this is a really sneaky trick, because the only vertical line we already know how to reflect in is the y-axis. So if I translate everything by minus a, I've moved x equals a, my intended line of reflection, to the y-axis, which is the only vertical line we already know how to reflect in. Then we can perform the reflection in the y-axis, which we know how to do, before undoing the original translation. Because we didn't do that original translation because we actually wanted to translate, it was a trick to move the line of reflection. So once we've used that to actually perform the reflection, we undo that translation to restore everything to how it should be. So this is a particular structure that often shows up in mathematics. If we call the reflection in the y-axis translation 2, or transformation 2, and we call the translation by minus a transformation 1, translation by plus a is obviously the inverse of transformation 1, so we can denote it as t1 minus 1. And what we've got then is a transformation sandwiched between another transformation and its inverse. So transformation 2 sandwiched between transformation 1 and its inverse. And I've written transformation 1 to the right because if you think about writing the function here, clearly the rightmost transformation acts first. So this type of structure, something sandwiched between something else and its inverse, is called conjugation. And it's one of these mathematical structures that will come up all over the place and you'll encounter a great deal when you get to an undergraduate level. So since these three simple transformations can implement what we want, let's see what they do to y equals f of x. So when I translate by minus a horizontally, I replace x with x plus a, or x minus minus a. Then when I reflect in the y-axis, I replace x with minus x. Notice that it's much easier to see that it's only this that gets negated, rather than the a as well, because in the back of our minds we have the passive perspective. And then finally, when I undo that translation, when I translate by plus a horizontally, I replace x with x minus a. So I've got minus x minus a plus a, which algebraically is the same as f of 2a minus x. So if I put this in passive language, we can therefore see that the rule for translating, or reflecting rather, in the line x equals a, is that you replace x with 2a minus x. And because we know that passively the x and y direction transformations look the same, the rule for reflecting in the arbitrary horizontal line y equals a is going to be that you replace y with 2a minus y. So notice that if you did want an active perspective on the horizontal reflection, if I take y equals f of x and I do this, I get 2a minus y equals f of x. So that means I get y equals 2a minus f of x. It's better to memorize the passive version because from that you can obviously figure out the active version very easily. And remember, they have the same effect. They're just two different ways of thinking of the same thing. So now, for example, if you see that a graph has got x replaced with a number minus x, you'll realize that it is a reflection in a vertical line. And you'll be able to figure out what the vertical line is by matching the thing that x is being subtracted from with 2a. So for example, if x is replaced with 1 minus x, well, 1 is 2a, so that must be reflection in x equals 1/2. So these rules are really useful to remember. They also make it easier to study things like reflective symmetry in an arbitrary vertical line. So a really effective thing to be aware of when dealing with graph transformations at a university admissions level. I hope you found this video helpful. If you're interested in more videos on TMUA, ESAT, MAT, and the various tricks and ideas which can be helpful in these exams, do remember to subscribe. If you're interested in more comprehensive support with your test preparation, you may also like to visit our website, where you can learn about the programs we offer for these various exams.